Okay, so what we're trying to do in this question is we're trying to optimize an area. So it says here Adam has 150 meters of fencing to surround a rectangular pen. His property backs onto a straight river which does not require any fencing. So I kind of drew a little picture here. We have our rectangular pen, right, our little area. And the area inside here, inside the fencing, that's the area that we're trying to maximize. So we're trying to figure out what's the biggest area that we can enclose given that we only have 150 meters of fencing. So we can't just say the length is 1,000,000 and the width is 1,000,000. That's going to give us a super big area. No, we only have 150 meters to work with. So this is a real life problem that we could use because often we don't have like an infinite amount of materials to use, but we want to kind of maximize the ability of those materials. So we're trying to build the biggest area on the inside here. And earlier in my polynomial series, I talked about how we could do maximization and optimization problems with algebra, right? With getting into vertex form and completing the square. So the sound wasn't really working on that one. Some people's it was, some people's it wasn't on their devices, but I'll just kind of go over how we can do this problem using completing the square, and then I'll just go over the calculus version. So we always need two equations. We need an equation involving the parameter, in this case 150 meters, and then we need an equation for the actual area, the thing we're trying to maximize. So let's start with the perimeter here. The perimeter, right, is equal to, the perimeter is just kind of like summing up all of these outside kind of fencing strips. So it's going to be L plus L, because there's two L's, plus W. Okay, and instead of saying L plus L, we always just say 2L. Combine those like terms. So 2L plus our width, that's going to equal our perimeter, which is equal to 150 meters. Right, they told us that in the question. And now let's think about our area. Our area is the length times the width because we're dealing with a rectangle. But notice how on the right side, area is a function of two variables. But if we want to graph this or solve it, we want to get it so it's in terms of one variable. So instead of just saying like length times width, we can get either length or width in terms of the other variable. And that's where we use this equation up here. So since there's only one W here, let's move the 2L over. So instead of saying 2L plus W is 150, we can say that the width is 150 meters minus 2 times the length. And that's true, right? Because if we have 150 meters total, and we subtract 2 of these lengths, so those are gone, we're just left with this width over here. So this equation is helpful because instead of saying W here in the area equation, we know that W is also equal to 150 minus 2L. So we can just plop that in there. So it's going to be length times 150 minus 2L, because that's really what width is. And we're going to get L, or sorry, not L, 150L minus 2L squared. So you'll notice here, if we were to graph this, right, in this case, we could complete the square, find the vertex of this thing. We could find the vertex of this two ways. Okay, we could say, all right, well, I know that since the factored form was L and 150 minus 2L, the L intercepts are going to be 0, right, because we factored out an L, so it's going to be here. And 150 minus 2L would also equal 0, so L would be 75. So this would be 75 here. And then we know that parabolas are symmetric. So it would look like this, right? I'll draw it a bit better. Look like that. We're trying to maximize the area, so this is the area and this is L, right? The vertex would just be here. And since they're symmetric, it's just going to be half of 75, right? Because from 0 to 75, right in between that is half of 75. So this will be 37.5. And then we could plug that in for L to just get our area. Okay, but that's not really showing our work. It's a way to do it, but what we would really do is we would expand it out and complete the square. So I have a video on completing the square. I'm not going to get into it, but what you would do is you'd factor out this -2. So it would be -2 times L squared, and then this would have to be minus 75L. And then you'd have to get this into a square, right? B over 2 squared, plus or minus that, and then do all that completing the square stuff. But the reason I'm bringing this up is to show you a super easy way to solve this question is using calculus. Okay, and not super hard calculus. It's called critical values. So if we're like trying to maximize this area, right, what we're really trying to find is the vertex of this thing. Because the vertex is going to tell us the highest point at which the area can get. And that's at the vertex, right? Right here. So notice that since this is a parabola, at the vertex, the value of this function's derivative is 0. Everywhere else, it's going to be positive or negative. So as we approach this vertex, it's a positive slope. And as we pass it, it's going to be a negative slope. But right at the vertex, it's going to be equal to 0. So since area, right, this is our area is just a constant. If we take the derivative with respect to L of both sides, right, or we can think of it as just saying the derivative equals 0, right, we just get 0 equals the first derivative of the other side. So this would be 150 minus 4L. Okay, so we took our function for area, we took the first derivative, and we said, okay, the derivative has a value at every point because it's differentiable on a polynomial over all real L values. But we know that the value of that derivative is 0 at the critical point, at the vertex, at its where it's at its very highest. If this was a positive parabola like this, the derivative would be 0 here. So if we were trying to minimize a function, we could also do that, right? That's where it's at its minimum. So now if we're just trying to solve for L, we add 4L to both sides, right? And this is just basic algebra from here. So we just divide by 4. L is equal to 150 over 4, which is 37.5, which is what we got if we were to just draw it out and think of it intuitively, right? So if this is 37.5, right, and he has 150 meters of fencing, that would mean that this has to be 150 as well, or 75, sorry. So notice that when we add these two together, that would be 75, and this is also 75. So since we're not worried about this part right here, the answer is always going to be equal to a square. So the area of the widths are always going to add to the same area as the lengths, right? Because the area of a square, in this case it's not a square because we have like the river there, but the area of a square is always going to be the biggest, like its area is going to be maximized. So this would be 5, this would be 5. If we only had 20 meters of fencing, those are the dimensions that we'd use. But in this case, it's a bit different with the river. So the main idea is just finding an area for the perimeter, or whatever equation involves your parameters. You get that equation in terms of one variable and plug that into your equation that involves what you're maximizing. And so you can get it in terms of one variable. And then you can just differentiate it, right? Set the derivative equal to 0 and solve. So this question here, what's the smallest perimeter possible for a rectangle whose area is 80 square inches? Okay, so if we say, I don't know, a rectangle here, right? This is our rectangle. And we know that the perimeter has to add to 80. Let's call this width, length, width, length. Okay, we're really saying that the area is 80 square inches. So remember, in the above question, we always started with the equation that involved the parameter. So right now, this is our parameter, 80 square inches. So the length times the width, that's the area, is going to equal 80. And in the last question, we also went over, we have to get this equation in terms of like one variable on one side and one variable on the other side. So let's solve for, I don't know, let's solve for L. We're going to get the same answer either way, but let's say L equals, we're going to divide by W on both sides. Okay. Now, what we have to do now is take this equation, L equals 80 over W, and input it into our equation that we're trying to maximize. So in this case, we're trying to minimize the perimeter. Well, what is a perimeter? It's going to be, oh, I drew this wrong. is going to be length and length, width and width. There we go. The perimeter is going to be 2W's plus 2L's, right? Because we're really just adding all the outside lengths together. And instead of writing 2L, we know that L is the same as 80 over W. So the perimeter is equal to 2W, because we still have everything in terms of W, plus 2 times 80 over W. Now 2 times 80 is just 160, so it's 2 plus 160 over W. So this is the perimeter. Okay, and we're going to assume that W is greater than 0, right? Because if the width is negative, that makes like no intuitive sense. So what we do now is we're trying to minimize this. So like we did in the last question, we're going to take the derivative with respect to W of everything, or we could just imagine it that the critical value is going to be 0, right? And we're going to say the derivative of the right side is equal to 0. So the derivative of the right side with respect to W is 2 plus, well, let's think here. 160 over W is the same as 160 times W to the negative 1, right? So this is really negative 160 if we take the derivative. This is negative 160 if we bring this negative 1 down, times W to the negative 2, because we're reducing that exponent by 1. Or in other words, it's just negative 160 over W squared, right? So it's going to be 2 minus 160 over W squared. Okay, and what we do now is we have an equation like this where we have a constant on the left, which is 0, and we have a variable on the right. So anytime we have a constant on one side, a variable on the other side, we're going to want to just use algebra to solve for it. So essentially, we're done using calculus right now. All that we're trying to do is solve for W. So I'm just going to grab my calculator here. Okay, so 2 minus 160 over W squared is 0. Let me just add 160 over W squared on both sides. So that equals 2. And now, let's see, we can multiply by W squared on both sides. So 160 is 2W squared. We can divide by 2, right? Just trying to whittle it down so we just have the W there. So 80 is W squared, okay? And now if we take the square root of everything, right, the left and the right, we're going to get the square root of 80 equals W. And notice how I don't have a plus or minus here, because if I said minus root 80, that would imply our width is negative, and we can't have a negative width. Okay? So just to simplify this, the square root of 80, we can write this as the square root of 16 times 5, and the square root of 16 is 4, so this is going to be 4 root 5. Okay, so the width is 4 root 5. Okay, and if the width is 4 root 5, we can find the minimum perimeter by just plugging that into our perimeter equation. So I'm going to erase this. Maybe I'll erase this here. So remember, our perimeter was 2W plus 160 over W. That equals our perimeter. Well, now if we know that the width is 4 root 5, 2 times W will just be 2 times 4 root 5, so this will be 8 root 5 plus 160 over W. This will be, well, 160 over 4 is 40, so this will be 40 over root 5. And if we wanted to rationalize this, we'd multiply by root 5 on the top and the bottom. So this would be 8 root 5 plus, well, it would be 40 root 5 over 5. 40 over 5 is 8. So this would be 8 root 5 plus 8 root 5, so that would be 2 times 8 root 5. So I guess 16 root 5. But what we really do is we our initial equation involves a parameter, which was 80 inches squared in this case. And then we get our equation for the thing we're trying to maximize or minimize. Use some calculus, bingo bango, we're done. Okay. Last question here. A rectangle lies on the x-axis and its two upper vertices touching the curve y equals 49 minus 3x squared. What dimensions would the rectangle need to produce the largest area? So what we have here is kind of a different looking question. It's involving an actual function to start out. So if we imagine the function 49 minus 3x squared, it's going to go up to 49 here and go down like this, right, because it's a negative parabola. And what we're doing is we're saying that its two upper vertices, like of the rectangle, touch this curve. So we can imagine that there's a rectangle kind of touching the curve here. Okay, so now that we have this, and we know that the vertices are right here, we can call this length x. We can call each of these lengths x, and the height of this rectangle is just going to be equal to the height of the function, right? Because it's touching the curve. So its height, we can just call it y, because the height is just the y value at that given x value. So the area is going to be equal to x times y, because it is a rectangle, right? So, and when we say area, we mean the area of like half this thing overall. So since this parabola is symmetric, we can solve it on one side and just double it. And that's going to be our answer. But when we say area, we just mean one side. Okay, so instead of, well, let's think about it here. Instead of y, right, I told you that y was the same as the function's height. And this is the function here, right? In the question, it explicitly says y is equal to 49 minus 3x squared. So instead of y, we can just say 49 minus 3x squared. And expanding this, we get 49x minus 3x cubed. Right, so this is our area. And what we're doing now is we're taking the derivative of both sides with respect to x, so it's going to be 0, right? Because if we were to graph this function here, it would be a cubic. We want to find where its slope, its derivative is 0, its critical point. So this will be 49 minus 9x squared. Okay. And once we have this, what we're going to want to do is solve for x. So we would add 9 on both sides. So 9x squared is 49. Okay, so these numbers aren't going to be great, but it's okay. X squared is going to be 49 over 9. Square rooting both sides. This will be, oh, it's actually not going to be bad. So x is going to be the square root of 49 over 9. And remember, like the square root of 49 over 9 is really just the square root of 49 itself divided by the square root of 9. So this is equal to 7 over 3. That's actually not a bad number. Okay. So now that we have that, that's what our x is going to be. Okay, so if we want to find the height of this function when x is 7 over 3, all we do is plug in 7 over 3 where we see x in this equation. So we know our y is 49 minus 3x squared. So plugging in 7 over 3 for x, we get 49 minus 3 times 7 over 3 squared. So this will be 49 minus, 7 over 3 squared is going to be 49 over 9. So 3 times 49 over 9 is 49 over 3. Right? And if we use our calculator for this, we could get it into a single fraction, but 49 minus 49 over 3, that's going to give us 32.7. So this is the area for this kind of strip right here. And if we wanted to area the whole thing, we would just double it. So doubling that, what would that be? That would be like 60 65.4. This would equal 2 times 32.7. So this is the total area. Okay, so even though the sound was kind of wonky from my first optimization video, I hope that this kind of helped you like using calculus and using completing the square. Like for this first one, it would be the same for all of these. Like once we have this equation, we couldn't really complete the square because it's not a parabola. But for this one, oh yeah, we couldn't do that one either. But so we would need calculus for these last two. But for the first one, this is kind of the same as all the other optimization ones I did in my first video, right? We have our area in terms of L squared, right? We would just find the vertex of that by completing the square, or we could take the first derivative, right, and set it equal to 0, solve for our variable. So not too difficult. In my next video, I'm going to be talking about related rates. So it's a bit different. It's not the same as optimization. I think it's probably my favorite unit in terms of derivatives, just because it has such a cool application to the real world. So I look forward to seeing you there, and drop a comment if you have a question. Thanks for listening.